Today's farmers face many challenges. In our global economy, farmers face competition not only from neighboring farms, but from farms halfway around the globe. Catfish farmers in Mississippi, Alabama, and Arkansas are feeling the effects of this competition. Catfish is a mild-flavored whitefish that has been a favorite of Southerners and others for many years, but its reign is being challenged by other imported fish like tilapia and the Vietnamese catfish, besa, which have similar qualities but cost significantly less in the marketplace. As a result, United States catfish production has dropped nearly 50%, from 660 million pounds in 2003 to only 300 million pounds in 2012. In addition to increased competition from imports, the catfish industry has also been challenged by increases in the costs associated with growing the fish. Fish feed prices have nearly doubled in the last 5 years, and fuel and energy costs are also on the rise. In order to remain profitable, farmers must find ways to grow catfish more efficiently. Scientists from several universities have attacked this problem by developing what they believe are two production systems that are superior to current open pond culture: the in-pond raceway system and the split pond system.
For those of you that may not be familiar with standard catfish production techniques, perhaps a little background might be helpful. To put it in the simplest possible terms, there are 4 things a fish needs to survive. They need water, they need food, they need oxygen, and they need a way to get rid of waste. Most catfish farmers today use what's called an open pond production system. This means that all the catfish in the pond are free to roam wherever they like, much like free-range chickens would do in a pasture. The ponds are typically anywhere between 5 and 20 acres, and they range from 4 feet deep in the shallow end to 6 feet deep in the deeper end. The food for the catfish is provided via a floating pellet that's distributed out across the surface of the pond by a blower. They put it over a large area with the hopes that all the fish will have equal access to the feed. The problem with this is that most farmers run multiple sizes of fish at the same time, so we suspect that the smaller fish may not have as good access as the big fish to the feed. The oxygen in the water comes primarily from the algae that's present. These microscopic green plants during the daytime, then through a process called photosynthesis, produce food and then oxygen as a byproduct. So during the day, when the plants are photosynthesizing, the oxygen levels are rising. But at night, when the sun goes down, those same plants start to respire and use up the oxygen. So what you'd see if you measured the oxygen levels throughout the day and night, what you'd see is that it goes up during the day, and then once the sun goes down, it starts going down and then goes back up and down. So what you'd have is a wave. At times, the biological oxygen demand from the fish, the bacteria, and the algae that require more than is produced during the day. At these times, farmers use mechanical aerators to supply extra oxygen. These paddle wheel aerators throw large volumes of water just a little bit into the air and break it into small droplets. That way, the oxygen from the air can easily diffuse into those droplets. Those aerators create quite a current also to help move the oxygen around the pond and mix the water. The waste in the pond that's produced by the fish is primarily taken care of by the bacteria that's in the pond as well as the algae. The fish produce ammonia, which is broken down into nitrite, which is still a toxic product, and then into nitrate through a process called nitrification. The algae can make use of nitrite as a fertilizer, so it works very well as a system. We feed the fish produce waste, and the waste fertilizes the algae, which produces the oxygen. So it works as a very nice cycle and provides all the things the fish require.
In an open pond system, all of these processes take place in the same space. Scientists have found that by separating the fish management area from the waste processing area, it is possible to improve both processes. This separation technology is not new and has been evolving for several decades. In the mid-1990s, scientists at Clemson University predicted that, quote, future pond aquaculture will move from farming the waters to true production systems in which manipulated ecosystems, the ponds, are redesigned into a series of more controllable fish production and waste treatment processes." Unquote. The first pond-based examples of this separation technology occurred in the 1980s when farmers in Arkansas began to experiment with separating the fish-growing area from the waste treatment area. Kelly Farmer at Arcat Fish Farm linked several ponds together and placed a set of concrete raceways between them. The water flowed from the upper pond through the raceways and into the lower pond. The water then circulated through several other ponds where the fish waste was assimilated before being pumped back to the top pond where it could be reused. This innovative approach was embraced by researchers at Clemson University, who developed what is called a partitioned aquaculture system, or PAS. The basic premise of the partitioned aquaculture system was to physically separate the fish culture unit from the wastewater treatment unit to facilitate better management of both fish production and waste removal and treatment. The design turned the pond into a long, narrow channel that coupled high-density fish culture raceways to an algal growth basin. Only 5% of the total area was used to contain the fish, while 95% was used to treat the waste. This long, narrow channel was similar to that used by sanitary engineers in wastewater treatment plants. The water was moved through the channel using a slow-moving paddle wheel. The shallow algal basin, combined with continuous mixing, allowed the whole water column to be exposed to the sunlight. This allowed for greater oxygen production and waste removal. A second-generation PAS system was designed for scaling up to commercial levels. This version used a wider and shorter algal growth channel, which reduced the cost of construction. A second set of large paddle wheels were added, so the water velocity in the algal channel could be controlled independently of the water flow in the fish raceway. This addition meant that not all of the water had to pass through the fish raceways. When the oxygen levels were high, more water would circulate through the raceways, but when oxygen levels were low, less water would pass through the raceways, and additional aeration would only be required in the small raceway section to maintain the fish. The second-generation design that was ultimately patented in 2001 also included computer-controlled gates within the fish raceways that could direct or divert water between the raceway cells. The idea was to have a filter feeding fish, like tilapia, in the center raceway that would feed on the algae and provide an additional income stream. The designers also thought that the continual harvesting of the algal bloom by the tilapia or a mechanical harvester would help keep the algae bloom healthy. A healthy bloom would minimize system crashes, help suppress blue-green algae that can cause off-flavor, and ensure that there was a net oxygen gain from the algal growth area. Trials with research-scale PAS systems showed that it was possible to produce significantly more pounds of fish per acre than traditional pond culture. When non-fed tilapia were added to the production figures, total production reached 15,000 to 20,000 pounds per acre. This was substantially more than the 3,000 to 5,000 pounds per acre produced in open ponds at the time. Unfortunately, the complexity and cost of the PAS systems prevented them from being adopted by mainstream catfish farmers, but they provided the groundwork for future systems that would be more compatible with the existing pond infrastructure. Both the split pond systems, developed by researchers at Mississippi State University and the Thad Cochran National Warm Water Aquaculture Center, and the in-pond raceway systems designed at Auburn University, incorporate the best elements of the PAS technology. In the next two segments of this video, we will take a more in-depth look at both of these systems. For more information about PAS technology, please refer to the Southern Regional Aquaculture Center publication number 4500, Partitioned Aquaculture Systems.